So yes, now that you've been softened up by the events of the day, I would like to talk about sort of taking this bounds philosophy and trying to make it sort of more useful. If you, as it stands, when you do bounds, the bounds tend to be fairly wide, which, I mean, as you saw in some of the worked examples, that can still give you very real sort of findings. And what's really nice about it is when you do have findings with bounds, those findings are built on a very low assumption foundation, which makes them easy to believe. But the price of that is the bounds are, in some sense, not very powerful. It's easy to have a lot of circumstances where when you do the bounds include something very negative to something very positive, and you're like, my treatment effect is something. And that doesn't tend to inspire a lot of people. But it turns out, so we've been playing with ways of sharpening these bounds and by using other information. And the other information that we use is going to be in the form of covariates that are predictive of something. So this is research. I don't know, Lindsay has probably already said this, but there's sort of a group of us that have been sort of focusing on principal stratification in the context of education. And this work comes out of that. And the running example that I'm going to be using is an example called early college high schools, which are basically these high schools. They're sort of small schools, and they're usually in partnership with a university. And the idea is the kids go to the schools, and the schools are sort of getting the kids to be taking university level classes as part of their high school education and try to make that transition from high school. You can sort of think of it as they're going to try to trick the kids to going to college by sort of not telling them they've left high school and entered college, and then they'll just end up in college in a very natural way. And these are entered with a lottery, so students would sign up and when they're in middle school to try to get into these schools. And there's a wait list. They randomize. Some of the students get into these colleges, or early college high schools, and some of them just go basically to their district school. And so we have this effective randomized experiment so we can actually look at the impact of these colleges as compared to the alternatives, which are these local publics.
I'm sorry, are these considered academically rigorous? Like in New York, they have these, and they're very desirable.
So these are considered academically rigorous, but they are serving, they're tending to serve, as you'll see, I think, they're tending to serve low-income students and students. So the quality of these schools varies, and the quality of the public schools of the students involved is sometimes quite low. So I would say that they're not like magnet schools. It's more of a charter school kind of model in that sense. So these schools were studied. There's 44 lotteries. There's 19 schools across 6 years. It was done in North Carolina. Oh, I see what this is. Excuse me. And so here's just a picture of North Carolina. The green dots are the various schools. Come on. So if you look just on ITT, so there were ITT effects, and we talked about grade 9 on track in the small schools of choice, same measure in this situation, and there was found to be a 6% impact on average going to the early college schools versus the local publics across all of the schools. So schools seem to be effective, which is nice, and I'm going to be focusing on grade 9 on track, and the idea here is to get a more nuanced picture of what this overall effect is. So we're going to do it with the principal stratification model, and I'm going to run through just as yet another tour through building principal strata and stuff. I'm just going to run through it. And I should mention that you should stop and ask questions, or look impatient if I'm going too slowly, ask questions if I'm going too fast, do something. Show me that you are alive. So the principal strata, sort of 3 types of school that a student can go to. And there's the early college high schools, which are the treatment schools. And if a kid doesn't go to such a school, they're going to go to a high quality school or a low quality school. there's a lot of work to decide what high quality and low quality means, and there's some evidence that it's hard to tell what a high quality or low quality school is, but we can do it, and we're going to dichotomize a bunch of variables to sort of create this measure of like good, bad. And then the research question is, to what extent do the effects of early college high schools vary according to the quality of the school students would have otherwise attended? So this is very similar, i.e. identical, to the Head Start Impact study in terms of the setup, where we want to say, okay, these kids, like, are these impacts happening to kids that would be going to high quality schools? Like this overall impact of 6%, is that due to the kids that would otherwise go to high quality schools doing better, or is it primarily due to the kids that would otherwise go to a low quality school doing better? What's the trade-off, right? Because that 6% could be, for one group of kids, we have a 13%, and the other group is 0. I mean, it could be a negative and a positive. We don't know. And so we want to find out. Generally, the students did attend very different types of schools. You'll notice that treatment, the compliance is really good. For the early college high schools, like 86% of the treated kids actually went to an early college high school. These here are basically ones that turned down their offer of treatment and stuck with a different school. 11% went to low quality, 3% went to high. On the control, you can see that in the absence of treatment, low quality schools are far more prevalent than high quality, given our quality measure in this population. Most students are on track in this population, however, so this is higher than small schools of choice. Treatment, on the treatment side, overall, like 94%, so almost everybody, and in the control is 88, which is still quite high. And remember that, because it turns out, just moving forward with your lives, that when you're near the extremes of a boundary, that's when the bounds are easier. You sort of have an easier time with the bounds, because you're sort of smushed up against a boundary, which sort of limits your possibilities. So you're going to end up with tighter bounds, generally, as a rule of thumb. So we can do our principal stratification. We make our boxes, our 3 by 3. And if we assign them the treatment, they go to one of these 3 places. If we assign a control, they go one of those 3 places. So there's going to be 9 types of kids, potentially, that we can conceive of. And I'm going to call them, like, EATs are the early college always takers. And then we have the, I don't know how to pronounce that, low quality always takers, high quality always takers. And then we have the low quality compliers, the ones that would go to a low quality school, then go to an ECHS school, and then high quality. And this actually, given these data, it's fairly natural, because people, the kids are in some middle school, and middle schools are usually feeders to a high school. And only if a kid sort of deliberately steps off the path are they going to sort of not go to sort of the school in their area. So what that means is you have this flow of, like, kids are, in some sense, given their social context, like where they live, they're going to be a low quality complier or high quality complier, and most likely because they're sort of in a place where their option is a low quality school, or their option is a high quality school if they don't get into the ECHS school. Then we have some defiers, which we're going to say don't exist. And then we're going to say that the treatment, the irrelevant alternatives, just offering someone an ECHS slot isn't going to suddenly cause them to change their local public school, right? I mean, I guess it's possible if they get the offer and then they decide to move based on that, or decide to look for a different charter school based on that or something, but it seems generally unlikely in this context. So then we have 5 principal strata left, and we want to understand them. And so the question is what we're going to estimate and what's all mixed up. So to get our complier average treatment effects, we basically need the mean outcomes of our LQC group and HQC groups under the control, and we need the mean under treatment, right? Like, as soon as we have those means, we can take the difference, and that's the treatment effect. And for the control side, if we go back, oops. For the control side, if we look at this, let's look at the high quality. If they're assigned to control, then these folks are going to go to a high quality school, and then the high quality always takers are going to go to a high quality school. But then from the treatment side, the only people going to a high quality school are going to be these always takers. So we can learn about the always takers by looking at the half of our always takers is going to be treated, half of our always takers is going to be controlled because of the random assignment. And on the treatment side, we're going to look at our half that are assigned to treated, and we're going to learn about them. And we're going to say, okay, they're doing this well. This is their mean outcome, whatever. And then we're going to say under the exclusion restriction, they're not affected by treatment. So the half of the always takers under treatment are going to look, their outcomes are going to look just like what their outcomes would be for the group that's in control, right? So we've divided our always takers into two groups, and these groups are equivalent. We're going to look at one to learn about the other. Once we know about them, we can then subtract them out of this mixture, and what's left over has to be our high quality compliers under control. And I'll do that mathematically in just a second. So that's the control side, is doing that game to get rid of the always takers. And then on the treatment side, we can get rid of our EATs, our ECHS always takers, using the same trick, because we get to see them by themselves in the control side, right? But the low quality and the high quality compliers are mixed up, and there's nothing that lets us separate them. So we're looking at a group of students, and we know that some of them are low quality compliers, some of them are high quality compliers, but we don't know which is which. And the bounding exercises, we're going to say, okay, we're going to look at these students, we're going to put sort of all of the high performing students, we're going to say is all of the high performing students, let's pretend they're low quality, and we're going to see what happens. We're going to say, let's pretend they're all high quality, and we're going to see what happens. So by looking at this fixed population and moving students, labeling students one way or another, we can look at a sort of a range of possibilities as to what the treatment effects might be. And that's the heart of bounding, is you just sort of say, I have this mixture, I'm going to divide this mixture into two pieces and see what happens. Like, if these are like this, then this happens. If these are like that, this happens. And you sort of make a list and you look at all the ways that something can happen, and that's your set of possibilities. So there's two kinds of important things about bounds that I'd like to underscore with this. The first is with always takers cause troubles with estimation, and they make things look more impressive, so you can feel fancy. But fundamentally, you can get rid of them, right? Because usually with always takers, you see them as soon as you sort of say defiers don't exist, basically. You get to see always takers by themselves. And when you see always takers by themselves in one of the two treatment arms, you can learn about them. And once you've learned about them, you can pull them out of your estimation problem. So they're not hard. What's hard is when you have two groups where you can't separate them. You can't figure out who is who. So always takers are a nuisance, but it's not the end of the day. Just to illustrate what data might look like, what we observe, you can sort of look at all of your students and you can calculate sort of summary statistics. So in this table, this is sort of an illustrative table, we have Z is our treatment, S is the school attended, and N is the number of students, and then Y, SZ, and then PSZ. So these are estimates based on some fake data in this case. For example, this is the group of people that were assigned treatment and went to an early college high school, and we had 570 of these people. And they're on track. They were 97% on track, and they represent 85% of the treated sample. So these three numbers add up to 100%. For 0.E over here, there was only 19 people, and their YZ was 0.98, so they're almost 100% on track, and their probability, or their proportion of the control group was 3%. So just looking at this table, what percentage, if you had to guess, what percentage of the students are, how do I want to put this? What percentage of the students would be low quality always takers?
$11.
11%? Why?
That's what the percentage is for the group that was assigned and opted local.
Yeah, so if we look, this group right here, this is the group of people. There's 76 students. We said, hey, go to an ECHS school. They said, no, I'm going to go to a low-quality school. And if you think back to our table, the only students that would have that kind of behavior would be low-quality always takers. And they represent 11% of the treatment group. And since the treated and control groups are basically randomized, that's an estimate of sort of overall. We would estimate that 11% of our population are low-quality always takers. What about ECHS always takers, the EATs? What percent? %, right? They're the ones that we don't offer them treatment and they go anyway, right? So they're the top row and there's 19 of them and they represent 3% of the treatment group, which is an estimate of overall, right? So, okay, now just roughly low quality always takers, which students seem to be doing generally better? Low quality always takers or the early college always taker or ECHS always takers? Why the ECHS?
Because their outcomes are higher.
Yeah. So what we're seeing here is the ECHS students, for whatever reasons, it might be because they're in the school, or it might be just who they are doing great. Almost all of them are on track. Whereas the low quality always takers are here, only about 82% of them are on track. So they're doing a little worse. Okay, any questions just sort of, so this is just basically the raw data. And from the raw data, we can directly learn about some of the groups, mainly the always takers. But some of the other groups are a little more nebulous. For example, if I said, how well are the low-quality compliers doing? Well, first you'd have to say under treatment or under control, because we expect them to be different under treatment and control. And where do they show up? Well, so which two groups in this table contain low-quality compliers? These two, right? The low-quality compliers, if you don't give them treatment, they're going to obediently go to a low-quality school. So these 554 are a mix of low-quality compliers and low-quality always takers, right? So some of them are always takers, some of them are compliers. And we can figure out, and that represents 83% of the low-quality people, of this group, is 83% of the population. And we know that the low-quality compliers is 11%. So if we subtract 11% from this, we get 72%. So 72% of our sample must be low-quality compliers. So this is an example of like backing out the always taker information to sort of learn about the compliers that are sort of hidden. Does that make sense? Okay, so next I'm going to show a sketch of some math, which is more pixelated than I would like. Is it more or less legible? More or less. All right, I'll go with shakily yes. So y bar 1 sub LQ up here, that is the mean outcome for the students that were assigned treatment, that's the 1, and went to a low quality school. So these are the low quality always takers. And we have that. And then we want to know, and we also see y bar 0 LQ. That's this here, like 83%. And we see that, and we know that this number is a weighted average of the low quality compliers under control and the low quality always takers under control. And this ratio here is like what fraction, this is pi LQC, like how many low quality compliers we have divided by how many low quality compliers plus low quality always takers. And then this is the number of always takers. So you can actually think of this as just a weighted average of some number of students. The mean of the low quality compliers under control times their size, mean of the low quality always takers times their size equals the mean that we see. And then some algebra we just sort of subtract and we solve for the thing we want, which is the mean of the low quality compliers. And we end up with this expression, which is in terms of the table before, which is these p's. P0LQ is like the proportion of the size of the group that was assigned to control and went to a low quality school. And we see that it's basically a function of these two means of these two groups. And what we're doing here is we're saying, here's our always takers, 82%, and here's our mixture, 83%. So we know that this mixture is a weighted average of the compliers and the always takers, and we know what the always takers is, so we can solve for what the compliers is, and we get a number, which is probably going to be close to 82, right? Like if these are 82 or 80-something-ish, and this is 80-something-ish, then this average with something else like this has to equal 83. It's going to be something close to 83. Okay, so that's just a taste of, like, algebraically how you can sort of get rid of always takers and and focus on a different problem, which is just this mixture of low quality and high quality compliers. So if you don't think about the always takers, then we see their mean outcomes and proportions under the control condition. So basically, if you don't have any always takers, under control, the low quality compliers conveniently go to a low quality school, the high quality compliers go to a high quality school, and you can just look at them. So that's good. But under the treatment, you just have this amorphous blob. And you want the two means that average out to this amorphous blob. You see the mean of them all together here, right? Like this mean, if there's no ECHS always takers, then this number right here is an average of low quality and high quality students. So how do we separate that? Well, geometrically, do I want to do this? Do you want me to do this? Should I pretend this never happened? All right, I'm going to do it because you're all just sort of staring at me. It makes me nervous. Okay, so think of, this is basically a Venn diagram. So the whole big circle is everybody. Or because remember, we've gotten rid of all the always takers. So the whole big circle represents all of our low quality and high quality compliers. And some fraction of the big circle did well. They got a y equals 1. Right? So the area, if the whole circle is 1, then the area, or the fraction of the circle that's shaded, is going to be y bar sub 1e, namely the mean of the outcomes of the people that went to the ECHS school, if we're ignoring the always takers. So what we're seeing here is, like, what fraction of these students got a 1? That's this shaded area. Now, the orange shaded area is what fraction of the students are low quality compliers. And now, we can estimate that as well, because we can, using the proportions that Lindsay talked about before. So we know what proportion of the circle has to be low quality compliers, and we know what proportion of the circle got a 1. And so basically any way you can shade in your orange, overlapping or not with your black, is a possible scenario that could be true, right? So we could have drawn the orange. Here, let me try. Well, that didn't work. That didn't work at all. All right, so we could have drawn the orange here. And then in this scenario, if this was the low quality compliers, we're saying that none of the low quality compliers got a 1 under treatment, that all of the 1s were the high quality compliers. And that would tell us that, so under this scenario, the low quality compliers would have a mean of 0 for their outcome. So that's one model. We can also, like, it could be this. It could be all of these are the low quality compliers, in which case all the 1s are the low quality compliers, and so low quality compliers had an average of 1. And that's also possible. So just geographically, because we can draw both of those pictures, we know that the mean of the low quality compliers under treatment could be anywhere from 0, i.e. none of them had a 1 outcome, or none of them are on track, to all of them are on track, which is pretty lousy for a bound, but that's what this picture would suggest. Yeah. Yes. That's exactly right. So I was just trying to be faithful to the size of the red, right? So because you're exactly right. So now let's do the high quality to illustrate your point. the high quality compliers, okay, is this big area, the area that's not shaded in. And there's no way to draw that big area to be entirely without ones. And there's no way to draw the big area to be entirely without zeros, right? Like the big area, if we oriented, here, let me put the, if we drew the big area like this, if these are our low quality, that's the best we can do. If we pack the low quality with a bunch of zeros, the high quality still has a bunch of zeros in it. And so the best case scenario for the high quality would be whatever fraction of the remaining area is shaded in by the solid area. And so that's one end of our bound. On the other side, if we put it over here, then we still can't get all zeros, but we can get mostly zeros, and then that would give us some lower bound. So the constraints, basically the constraints of bounds are dictated purely by the geometry. And you can sort of draw a picture like this and play around with it to see it, which may or may not be helpful depending on how your brain works. But so the way I've conceptualized this is we have this and we have this, and we're going to let Q be the fraction of the kids who are low quality and have a 1 who are on track. And then given that, then the mean that we're interested in is Q divided by the total number of low quality compliers, or the total fraction of low quality compliers. And then how big can it get? Well, it can get as big as, it can't get any bigger than the number of low quality compliers that we have, and also can't be bigger than the total number of ones we have. How small can it get? Well, it can't get any smaller than 0, right? This like overlapping thing, it can get as small as 0, but it can't be negative, and also can't be smaller than the white space minus the other white space. So it's like the inverse of the problem, which gives us this. And that's what gives us our bounds. So that really is what's behind the bounds. Oops. When you do that, you get this expression for your bounds. So with no always takers, we say that your treatment effect is going to be your low estimate of your outcome under treatment minus your estimated outcome under control, or your outcome under control. And it's going to be less than the highest possible outcome under treatment minus the average outcome under control. And then here are these bounds, these mins and maxes that we just saw. You can re-express those in terms of the original data that we saw. And I'm not going to dwell anymore on that. OK, so here's another visualization. Here's a hypothetical population where we actually know who the low quality and the high quality are. The blue is the outcome of 1. The white is outcome of 0. And let's say the picture looks like this. So we have perfect information. But what we actually see is just sort of this mass. For any particular student, we can sort of think of that as we know sort of on average what their outcome is, but we don't really know who's low quality or high quality. So we see in this case, in my hypothetical example, we're going to see 58% of these dots are on track. And we also know that 60% of the dots are low quality, or low quality compliers. We shouldn't say that they themselves are low quality. That would be mean. But so our worst case would be all of the ones, all of the on-track people are low quality, so we move all the dots over here. And then the other version would be try to move as many of the dots on this side. We can fill all of this, and we're going to have a few dots left over. But in this case, our lower bound on high quality is 0. And if we flip it, it's the other way around. All right. Oh, and for reference, I think they're in your slides. With always takers, I just want to point out that with always takers, it just makes your formula more complicated, but it's really the exact same thing. And what you can see is this stuff right here is the backing out of your always takers. So you're still looking at this trade-off between your compliers, but to estimate all of the pieces of that trade-off puzzle, to build that Venn diagram, you need to estimate the components of the Venn diagram, and you just sort of do that by sort of subtracting off the always taker stuff. Once you've subtracted off the always taker stuff, you can then write down your bounds in terms of these indirect quantities. But then when you put it all together in the algebraic expression, you end up with sort of these extra little things floating around. And so this thing right here is basically a rescaled average outcome, and you're sort of moving the mass of your average outcome to one group or another. Just some intuition about this formula is notice that the way the formula is written, oops, I'm missing a very important part of this formula. No, that is correct. So if you look at the difference of these two things, the only difference between these two things is this b term is like this rescaled single number. And then the width of the bound can only be this wide, right? Because it could be less than that wide because we're sort of stuck up against 0 and 1. So you're sort of truncated by 0 and 1. If you're way up here or way down there, you're going to sort of be smushed up against the side. But if you're somewhere in the middle, this ratio is the width of your bound. And that ratio is the ratio of complier type. So if you're in a strata where you are most of the strata, then your bound is going to be narrow. But if you're in a, or like if the low quality compliers are a small fraction of everything, then they're going to have big bounds. If they're a big fraction of everything, they're going to have small bounds, which makes sense, right? Like if you're looking at an overall group and you know that this group is 98% high quality compliers, then you don't care what the low quality compliers are. They can be anything, and the overall mean is not going to change much. And so your high quality estimate's stable. But for the low quality group, that little 2%, if any, it's easy to make them all 0 or all 1, so you're going to get a really wide bound. So that ratio of complier types should govern your thinking about like when are bounds going to be good. Bounds are going to be good if like if you're looking at two groups, bounds are going to be good if one of your groups is much bigger than the other group. Then bounds are going to be good for the big group and bad for the little group. Does that make sense? Also, bounds are going to be good if you're smushed up against 0, then when you do this little min-max exercise, you might sort of chop off this big width because you can't go below 0. Similarly, if you're up near 1, this thing could easily be bigger than 1, which will again chop off your width above and make your bounds narrow. So basically, you're going to do a good job bounding if your group is really big relative to the other group, or you're almost always near 1, or you're almost always near 0, as a general rule of thumb. In ECHS, just our actual results, we end up with the low quality compliers, which were the big group if you recall. We see an impact of anywhere from 8 to 13% percentage points on track. So it's sort of a big effect for low quality compliers. The high quality compliers, on the other hand, have anything from a negative 33 to a 1% impact, which basically would suggest that it's like we can say definitively we're not helping the high quality compliers a lot, and we might be hurting them. But for low quality compliers, we're helping them. And when we looked at the overall treatment effect estimate, we're not really seeing that more complicated story. And so even with the bounds, even with these crude bounds, we see this more complicated story, which we can visualize as a trade-off, right? These are the possible treatment effects for high quality going from negative 33 to 1, and then the low quality sort of in this narrow band, which is really telling us that we don't know anything about the high quality people, but we know a lot about the low quality people. Just to step back briefly for like mechanism, this could be the counterfactual condition. The early college high schools and the high quality schools are basically equivalent schools. And therefore we don't see a treatment effect for the high quality. That's one scenario. Another scenario is the students that happen to be high quality compliers are bulletproof. You can put them in any kind of school you want and they're just going to do the same thing. They're school immune, say. Whereas if you put a low quality student into a high quality school, they might have some big benefit or who knows, right? Because they're different populations, we don't actually know about the mechanism, but it's suggestive, right? An easy natural explanation is the high quality schools and the ECHS schools are comparable in quality. Okay, yeah. Yeah. Well, this is the danger of bounds, right? Whenever you see a range of something, your natural inclination is it's probably in the middle, whatever the real thing is. And as soon as you do that, then you're not entirely being faithful to like what the bounds are saying. That being said, you're right. Like, because furthermore, for the high quality to have a positive effect, the effect on the low quality has to be as big as we can possibly imagine. Is that correct? Yes. Which suggests that I drew this line backwards. This is wrong. Somehow this line is supposed to be down like this. I apologize. I will fix this. Because it's a trade-off. The bigger the treatment effect in one group, the smaller it has to be in the other. So I apologize, this line should be going like this. I'm not sure why it's doing the wrong thing. I'll just pretend it's not happening. So this dot down here, so for the treatment effect, to answer your question, for the treatment effect for the high quality compliers to be 1, the low quality compliers would have the smallest of treatment effect in the range of like 8%. For the high quality compliers, the more we believe the high quality compliers effect is negative, the more we think that the schools are having a huge impact on low quality compliers. So there's this weird trade-off of like, you're right, like this is sort of an extreme, but this is an extreme that makes our two groups the most similar. So in some sense, maybe that extreme is more plausible than we think. Whereas way down here, we're saying that the effect is seriously detrimental for one group and as helpful as possible for the other group. That's sort of a harder sell. But again, it's a substance matter thing. My honest belief is, yeah, it's probably the case that the impact on the high quality compliers is slightly negative. I mean, that's sort of the most natural explanation given this collection of bounds. Does that answer your question?
Yeah,
or?
from a policy perspective, it would be very, like, to say that it's going to,
Yes.
it's a more nuanced picture that it probably helps, well, definitely helps have low quality, but probably hurts high quality is a much more nuanced picture than, oh, we don't know, it might not be positive for high quality, right? I mean, like, it's...
Yeah, so because I'm conservative, I guess I would go to the policy makers and say, if you're going to open these schools, open them near what you're calling low-quality schools, because these populations seem to be helped by whatever's going on, whereas the other populations, they're certainly like, it's not worth opening a school, because in the best-case scenario, we're doing nothing. But I agree that like it is suggestive. Like, should we close the schools that are serving? Because to a large extent, the schools themselves, well, there's a confound, which is different schools are involved, right? Low quality and high quality actually represent a variety of schools, and the high quality compliers are actually going to different ECHS schools than low quality compliers in general. So it might be that the high quality compliers are going to the worst of the ECHS schools. So you'd want to then look at sort of the school quality metrics of the ECHS schools and do something qualitative to try to get at possible mechanism. I mean, it's a very interesting question. Like, what do you do once you know? This is the sad thing about variation in treatment effects. Once you've established variation in treatment effects, people aren't going to be like, oh, that's great, and then stop talking to you. They're going to like immediately say like, why? And they're going to want answers, which is then you'll be, before you know it, doing mediation analysis and everything that entails. So, all right, but none of what I've talked about is what I was supposed to talk about. And now I probably only have 10 minutes to talk about what I'm supposed to talk about, roughly. So I'll talk about it, but quickly. But happily, it's a fairly natural thing to talk about, which is, say we had a prognostic covariate, like pre-test, grade 8 test scores. So we know these students. Some of the students we know are just like already doomed, and some of them are already doing well, regardless of where we send them. And so we're going to call it X3. And we can see that X3 is pointing the wrong way. But so down here, at this value of X3, our students tend to be on track. And as X3 gets higher, so I guess X3 is like the negative of grade 8 test score, then fewer and fewer students are on track. So we have this score that's predictive of how well a student is going to do. And we're going to use it to create 4 equal-sized slices of our population. Right, so we have like low, mid, high, mid, and high, say. And inside each slice, since this is a pre-treatment covariate, we can think of our overall randomized experiment as actually 4 separate randomized experiments on the 4 different groups defined by this covariate, which means we can do the bounding exercise in each of those groups separately with no regard to the other groups. So that's what we do here. So say this is what we see, then we can start, so within each strata, we can sort of pack all, like say we're doing one side of our bounds, we're going to put all of our on-track kids as much as possible into the low-quality group. So we're trying to get the worst picture possible for the high-quality group. Now, if you recall the first diagram, we were able to put all of the on-track kids in a low-quality group. But now, because we're forced to obey the stratification, we're doing this bounding exercise within each strata. These strata are the same. We still say, like, yeah, none of them, I mean, it's possible that none of them are on track. But for these strata, we say, actually, even in the worst case, some of them have to be on track. And so because we've sliced, so then we slice, and then we average over the slices. And you can just do it visually here. We know that there's 1, 2, 3, 4, 5, there's 24 high-quality compliers. 5 of them, at least 5 of them must be on track. So our lower bound is going to be 5 over 24. And similarly on low-quality compliers, we can't have almost everybody be on track, but we can get all the way up to, this is, what is it, 36 minus 6, so 30 over 36 is our upper bound for what percentage of the low-quality can be on track. So if we look at our calculations, we now have a bound of 21, a lower bound of 21% instead of 0, and we have an upper bound of 83% instead of 97%. So major gains just by cutting it up into little things and then recombining those things. I mean, yeah. So in this nicely designed artificial case, stratification is a great idea. So then what other kind of variables might we consider for slicing up our data? So that was a prognostic covariate. It told us how well a kid is going to do. It tells us about the kid's outcome. What other variables might we consider? Do you want to answer, Sean? Or are you just stretching?
No, I'm things that predict which strata.
Yeah, things that tell you what strata they're in. If you think back to that bound formula, what we've just done is we've looked at strata where we've made some strata that are packed up against 1 and packed up against 0, right? We've made some extreme strata, and in those extreme strata, we're better able to bound. But if you think about that original formula, the ratio of the two kinds of compliers also makes the bound, the more extreme that ratio it is, for one of the groups, it makes the bound really, really tight, which suggests that if we can have some variable that predicts, are you a low quality or a high quality complier, maybe you can get some gains. And that's exactly what it's like a propensity score, propensity to be a low quality complier. So in this picture, we have this propensity score. So we again have 4 strata, but now we're stratifying on x1. High values of x1 indicate that you're probably a low quality complier, given that you're a complier. Low values of x1 suggest that you're probably a high quality complier, given that you're a complier. These are the same dots, just under a different variable. So again, this is like if we had perfect vision and can actually see where everyone was, this is the truth. But we don't have the truth. We have to play our bounding game. So we're going to, like, again, shove all of our dots in each of our 4. We're going to move all of our dots to low quality as best we can and then look at our bound. We did this in the ECHS study. This was the proportion of the students' middle school cohort who went to a low quality school, because the middle schools are feeding into particular schools. So if we know a kid goes to this middle school, we're pretty sure that if they don't go to an ECHS school, they're going to go to that high school, and that high school is either low or high quality. So we had a very predictive covariate in this case. So here's a picture of our bounds. So for our high quality, we have this little teeny bound, or this little teeny slice, and the bound is bad in this little teeny slice. Down here, we have our big slice, and our bound is better in the big slice. And this rule of thumb generalizes. You're going to get tighter bounds in your bigger slices, and you're going to get worse bounds in your lower slices. But then when we combine the bounds in each of these 4 things, we combine weighted by the slice size. This slice is more important because it has more of our high quality kids. So we weight this slice more when we're looking at the high quality kids. Conversely, when we're doing the low quality, we're going to weight this slice more when we do the low quality versus this one. So it's this perfect trade-off of when we cut up based on these propensity scores, we're basically coming up with strata where in some strata are mostly high quality kids and we can do a good bounding job on them. And then some strata are low quality kids and we can do a good bounding job on them. And then there's some strata that we don't know and then we just do a terrible job for both. But hopefully we don't have too many of those strata. If we do the calculations here, then we see that we get a bound of 25% and 81%, which is a little bit better than before. But full disclosure, I kind of cheated. The first time I put this example together, this bounding didn't work as well as the first one I showed you. And then I didn't like that because that's not very exciting. So I changed it, and now it's better, right? That's statistics. So, but that does raise a question. Any guesses as to what the question is? Yeah, what should you do, right? So if I just told you that sometimes one, sometimes another, are there some good rules of thumb? Or like, is there some direction you should go? So there's two primary choices. There's the prognostic score and the propensity score. And here I'm showing you a different data set where I've sliced my data into 6 slices based on the propensity score. And what you can see here is in some of my slices, I have a really tight bound on low quality. X-axis is low quality, and y-axis is high quality. So in some, I have a really tight bound on low quality and lousy on high quality. And then here I have a really tight bound on high quality and a terrible one on low quality. So in this slice is basically, it was all high quality compliers. And there was just a few low quality, and so we're able to nail down the high quality. Low quality is this big wide bound, but there's actually not very many low quality people here, so we don't care. Right, so that's one style of how things work. For the prognostic score, you'll notice that the bounds are tight at the extremes. This is almost everyone was not on track. Here, almost everyone was on track, so it was near 1. And we see that the bounds are tighter. When we get into the middle, it's just sort of wide and vague. So those are the two variables sort of give you different kinds of trade-offs. To evaluate those trade-offs, we did a simulation study where we're going to just generate data indexed by some latent traits that govern school quality that you're going to go to, whether you're a complier or not, and what your outcome is generally. Like basically, the latent traits represent student ability, social context. And then we're going to stratify these covariates and look at the resulting bound widths and sort of look to see when these covariates are good. In case you care, our generation process is we have like 3 variables that are just normal noise. And then we're going to make a dummy variable whether you're in a high or low quality context, right? So like this is a dummy of whether you're in a good, like your local school is a high quality school. And then these are your potential outcomes of like what school you go to. And you'll see that the second variable is whether you're basically a complier or not. Just a general complier. And if this variable is really, really big, then even if you're assigned to the control condition, you're going to go to an ECHS school. So this term determines whether you're a complier or an ECHS always taker. And then here, you go to an ECHS school if this variable is bigger than this adjusted thing, which tells you if you're a complier, or you just go to your local school no matter what, which tells you if you're an always taker or a complier. Right? So these two things sort of decide whether you're an always taker, never taker, whatever. And then your outcome is just a logit model where you have your third latent variable times some coefficient, which is just like your tendency to be on track, plus a shift based on what kind of school you went to. So if you go to the different schools, you shift your probability of on track up or down. So we generated data where there was like a treatment mechanism. And the advantage of doing this, and then the omegas and everything like that, they're just like you adjust these numbers to get your marginal means and proportions the way you want. And so what we observe, and then what we do is what we actually observe is we don't observe the latent, we just observe an outcome x, which is the latent plus just some extra noise. And that gives us a knob to sort of say, okay, we're going to add more and more and more noise to the latent variables and see how the bounds collapse when we stratify on that variable. So you can say, okay, we're going to have a very noisy version of the prognostic score. What do our bounds look like when we stratify? If we don't have a noisy version of the prognostic score, what do our bounds look like when we stratify? So it allows us to systematically look at how bound performance degrades as we lose information. And our data basically looks like, for each student, we have our 3 X's, whether they're treated or not, what kind of school they went to that we saw that they went to, and whether they're on track or not. And then we just analyze those data using our code to do the bounds and look at the width of the bound. And here's our noise to get more or less useful X's. So bigger noise means our X's are less useful. So here's a picture for the low quality group in our scenario. And what we see is as noise goes up, so our variables are getting less and less and less useful, it makes sense, the width of the bound goes up. So the top, the red, is no, we're not stratifying on anything. We're just using the original naive method. And in this scenario, the bound width tends to be about 1, which is not great, right? It's slightly less than 1. So what we're seeing is if we don't do anything, our bounds suck. But if we stratify under different methods, so let's look at the green line. This is stratifying whether you're a complier or not. That doesn't really help you that much. The blue line tells you what kind of complier you are if you're a complier. No, the blue line is your outcome. And that helps more, right? Like in the least noisy case, when we have the strongest version of that covariate, our bounds on average are about 0.5 instead of 1 in width. So that's much tighter. If we look at the prognostic score that tells us what kind of complier you are, if we know what kind of complier you are, in the 0 noise case, that variable is basically telling us you're low quality, you're high quality, you're low quality. Not surprisingly, the bounds are almost 0 because we just know who's who, and we can just analyze them. As we add noise, though, the bounds get wider and wider. It seems, although it's hard to directly compare, that the prognostic, this one is the prognostic, gets worse and worse. However, the best is when we stratified on both the principal score and the prognostic score. Sorry, principal is the same as propensity. If we stratify on both the principal score and the prognostic score, then we get the tightest bounds overall. That was a botched job. Let that be a lesson to you all. When you have a legend like this, there's no way to tell what is what. So don't do that. It's terrible. It's very bad visualization here. Because, is this going with this or this? I mean, it's a disaster. All right, so I'll never do that again. All right, so here's the high quality group. I guess I did it again. But that's not my fault because it's only been a few seconds. But for the high quality groups, the story is the same, except there's less gain of all of these. Although the cross tabulation one where we make strata, which are basically, so what is this doing? It's saying we're going to find a group that is like really high performing low quality compliers, really high performing high quality compliers predominantly, really low performing low quality compliers predominantly, and like really low performing high quality compliers predominantly. When we do that, we get sort of tight bounds. We get sort of we get the double dip on that formula. We get a narrow width, plus we're sort of huddled up against one of the ends. So we end up with these tighter bounds, and then when we average over all of those, we end up with overall tighter bounds. On the actual data, no stratification, our bound width for like the low quality compliers was about 6 percentage points. But when we did by middle school, when we were predicting low versus high quality complier, it dropped to 2, and when we did both, it went to 1.7. Here, the prognostic score didn't help much. On the high quality complier side, we had a 34 percentage point width. You remember it was like negative 33 to 1. When we used 8th grade achievement, it dropped to 23%. If we used middle school, it was 13%, and then when we used both, it was basically still 13%. So there's slightly different stories here, but the winner is still both, like exploit all the information you can. That being said, it does seem like knowing who is more important than knowing how well they'll do. All right, so the conclusion is covariates can substantially sharpen bounds. Like, I think the covariates makes this whole exercise possible, especially because in many, many contexts, you have covariates that are incredibly predictive of either outcome, like a pretest score, or what kind of complier you are, what kind of principal strata you belong to. So because you have those things, it's using that information is critical. And that being said, propensity scores seem to be more effective than prognostic. In the simulation scores studies, propensity score is 1. There's a big caveat, though, which is like, in some sense, we're saying these two scores of if they're predicting the same amount, but one is predicting one thing and one is predicting the other. So it's hard to really compare, like, which is a better predictor. If you go back to these slides, for example, so here's our principal score, 1. And maybe we should be comparing the principal score with this amount of noise to the prognostic score with this amount of noise, in which case the prognostic score is more effective, right? Because like here at 0 noise, the principal score is giving us who's the compliers are, but the prognostic scores are still just giving us the probability of being a 1 or a 0, but there's this extra randomness that is making the prognostic score sort of less informative. And so it's getting a short end of the stick on the simulation study. So comparing is a little tricky. That being said, especially given the empirical example, it seems like it's easier to come up with variables that are very predictive in a useful way of compliance status. Yeah, so I think that's it. Yeah.
So typically when we think about like propensity scores, we have some sort of observed, say, binary treatment, and we fit a bunch of models predicted and we take this probability of lower propensity score. But you're not really doing that here because you don't know which kind of complier they are and you're not fitting a model predicted. Right? And using the predicted probability from that, you're just taking a covariate that you think from theory
Yeah.
is predictive of which kind of complier you are, but
You don't actually, yeah.
know how predictive.
Except you can make them. So setting aside the issue of always takers ruining your estimation life. So first, I shouldn't be saying propensity, I should be using prognostic, which is actually in the literature. There's some, like prognostic is, or sorry, not prognostic, principal is the, principal scores are used because it's principal stratification. So, and there's some estimation methods. So random caveat, we're showing you bounds here. And we mentioned these like Bayesian models as another way of fitting. There's yet another way of fitting where you estimate these things called principal scores, which are using covariates. You're basically doing a dimension reduction of your covariates down to a score, which is given your covariates the probability that you are a low quality versus high quality complier. And then principal score methods actually do sort of observational study reweighting of individual units to sort of create estimates. We're using them here to stratify, and you're right that in my simulation study, I didn't estimate them, I just sort of assumed I had one. But if you had a whole bunch of covariates, you actually can estimate them. There's extra uncertainty there, but you can estimate them by looking at your one arm of your treatment group or the other, and sort of regressing whether you have this kind of behavior versus the other kind of behavior. The always taker sort of muddies that up a little bit, but it's survivable. So the reason I'm using prognostic and principal scores is, in principle, you can get these scores based on some complicated kind of covariates in a very natural way. And what's nice about it is that activity is a pre-treatment activity. So even if your model is completely misspecified and you're completely wrong, that's only going to make your bounds less effective, but it's not going to violate the legitimacy of what you're doing. And I want to underscore that point, which is that the really nice aspect of these bounds, if they are informative enough to be useful, is they're built on nothing, basically. Like, it's an easy pill to swallow in terms of the assumptions. So it's very robust. You don't have any real assumptions to worry about, other than you really did randomly assign, and these assumptions about like these kinds of people don't exist, which are arguably sometimes big assumptions. But all of the other methods rely on that collection of assumptions and then a whole bunch of stuff besides. So like this is as sort of stripped down as you can get. And I think it's fair to say that we, advocate, like the group of people working on this, as like this is, the other estimation strategies are heroic. Like a lot of assumptions and a lot of hope that things are going well. So doing the bounds is a nice sanity check to make sure that you're not doing something totally insane. But yeah, I hope that answers your question in a roundabout way. Any other questions? I know I went through fairly quickly, and I'm happy to talk later. You can contact me or any of us. But also, if you have questions now, don't hesitate. You all want freedom. All right, freedom it is. Thanks.